So in yesterday's class, I mentioned about the utility or applications of transparent conducting materials. A very important class of wide band gap semiconductors, where the band gaps are anywhere from 3.2 to 3.4 electron volts. In reality, the band gap or the band gap energy is so high, that means the separation between the valence and conduction bands, the forbidden gap energy, they can be considered as insulators. Then when you start doping these systems, you've seen two examples where alumina, an insulator doped with chromium, starts showing those interesting optical properties. So you can make a laser out of it, because chromium doped alumina is ruby. And in yesterday's class, what I mentioned was another example where another versatile system, zinc oxide especially, it has a lot of applications in transparent conducting oxide coatings, where the top coating has to be both conducting as well as transparent. So when you call these systems as transparent conducting oxides, even though transparency is there, of course, above 95%, conductivity is also there, but these are not as conducting as metals, because metals are good conductors, we know. Copper is a very good conductor, but it's not transparent. I can't use even a thin layer of copper used as a top electrode that requires transparency. Copper cannot be used. Aluminum cannot be used. That's where you have these doped wide band gap semiconductors that can be really readily used as conducting transparent systems. So the example I started with zinc oxide, a wide band gap system with a band gap of about 3.4 electron volts. Now, when you dope it, you start seeing the creation of these mid band gap states. So mid band gap states can also lead to coloration of the material, and also because of the states that are created, if you have donor states, acceptor states, and also some defect states, depending on where these states are located, if they're shallow states, close to the conduction band and valence band, you can bring about conductivity into the lattice. Okay. To continue with that example, look at this nice example. I told you I have a small glass slide. Glass, of course, is insulating. And so a thin layer, about 60 to 70 nanometers of zinc oxide is coated on it. So the transparency of zinc oxide is also as good as, that of glass. So just see through. So, the coated film on a substrate is kept on these three letters printed on a paper. So you can clearly see the transparency of the film, along with glass, of course, we know is transparent. Okay. Now, yeah, this was the last part of our discussion, how you get conductivity. It happens in the following way. When zinc oxide is there, it's a charge neutral compound. Zinc has a valence state of 2 plus and O2 minus. So per se, zinc oxide lattice has no free carriers. Now, when you dope aluminum, aluminum is a trivalent element, right? So aluminum replaces zinc, and it brings an extra electron to the lattice. So that's a key here. Okay, that's how. So these excess electrons, I also mentioned again to reiterate the fact that the dopant levels are normally anywhere from 3 to 5%, not more than that. But that small amount of doping can cause such interesting changes in conductivity and optical properties, etc. Right? That's how electron comes in. If you replace zinc by another divalent element, it may lead to other interesting properties. For example, a magnetic element replacing zinc, a 2+ magnetic ion replacing 2+ zinc. You may start seeing changes in the magnetic properties, but this is a classic example of how you can bring in an electron into the lattice. Similarly, hole doping can also be done. All right. Yeah. Look at this small video that we have created for you to appreciate how conductivity and transparency both coexist. Okay. Now, this is glass, of course, right? And you see the meter here, it shows overload. Okay. Glass is non-conductive. And this is fluorine-doped TiO2 coated on glass. Fluorine-doped TiO2, titanium dioxide, has applications as TCO, transparent conductivity. You see that it shows 26, about 20.5 ohms. Okay, so from glass to fluorine-doped TiO2, certainly there is a huge change in conductivity. This is sapphire. I was talking about it yesterday. Alpha alumina is sapphire. It's transparent, but it is insulating. Alumina, it is made of alumina. But this is zinc oxide and sapphire. Okay, now you see that. It's about 14 kilo ohms there. You see, from a completely overloaded state, that means resistivity in giga ohms, the resistance changes by several orders, right? Now, this is a silicon substrate, P-type. You see 15 ohms there. Yeah, anywhere varies from 8 to 15 ohms. And this is diamond-coated silicon, and diamond is insulating. And obviously, what you're seeing is completely, it's overloaded there. And this is, boron-doped diamond and silicon. You see, the boron doping makes diamond semiconducting. See that? A completely insulating diamond. I'm playing it again. So we start with showing the glass. You look at the meter up there, overload. That means extremely high resistance. And then you have fluorine-doped titanium dioxide coated on the same glass piece. It shows 24 ohms. Very interesting, is it not? You see that you have transparency as well as conducting nature of the surface. Then sapphire, which is also transparent. This I told you in the last class. Alumina, alpha alumina is sapphire. But sapphire is an insulator because alumina is an insulator. So overload there. Okay. Now this is zinc oxide on sapphire. This is still not doped zinc oxide. Zinc oxide just with oxygen vacancies. That itself shows conductivity in few kilo ohms. So right, see that. Now if I dope zinc oxide with aluminum, the resistivity further comes down. The conductivity increases. That's second case, sapphire, bare sapphire, and sapphire zinc oxide on sapphire. Then silicon P-type substrate, typically a few mega ohms of resistance. Yeah. Now diamond on silicon, a thin layer of diamond on silicon. Diamond is insulating, but diamond and silicon is required for heat spreading applications. And this is boron-doped diamond, which starts conducting, right? See, so you can convert even an insulator like diamond into a conducting layer. right? That is the power of doping. Now coming back to the concept of doping. So I said now aluminum doping in zinc oxide brings about changes in conductivity. The earlier example was, and in thin film form, it has lots of applications. And in another example, we have seen how an optical activity can be induced by doping chromium into alumina lattice. Now, this is a typical case where zinc oxide is doped with samarium. See, most of the light emitting solids, luminescent solids, you have a host compound, host lattice. And the host lattice typically is a wide band gap system, like zinc oxide, zinc sulfide, calcium sulfide. These are all wide band gap semiconductors. All the light emitting solids that are used in display devices, they're wide band gap systems. But then the wide band gap system itself doesn't show luminescence. Now, you must have understood that with the examples that I've shown. So it needs to have a dopant, right? So alumina doped with chromium, we have seen the production of, lasing action, and you call it a ruby laser. Zinc oxide with aluminum, you see increase in conductivity. Now, what happens when zinc oxide is doped with an element like samarium? So samarium belongs to the family of rare earth compounds. You have 14 rare earths, and rare earths are very interesting in terms of bringing about a number of electronic levels in the forbidden gap of these host lattices. Okay, they create these multiple number of electronic transition levels. Now, when you have these additional transition levels, right? So the fundamental band-to-band absorption is modified also with the absorptions happening in the levels that are created in the forbidden gap of the host lattice. So that's the whole concept about color tuning also, right? Different elements bring about different types of levels. And also you have the crystal field of the lattice having an effect on these layers, right? The higher the crystal field, there's further splitting, the Zeeman splitting of these lines, giving rise to sub-emission bands. All these interesting things happen. And rare earth ion doping is also interesting from the point of inducing magnetism into the otherwise non-magnetic lattices. So many things can happen. Here is a beautiful example of what happens with samarium doped at zinc oxide. So when you dope samarium ions statistically distribute in the zinc oxide lattice. And again, the dopant levels are not more than 3 to 5 atom percent. Now, you see, if you look at the electronic transitions, there are some major transitions like the ones that happen from 4G 5x2 to 6HJ. These leads to emissions at those wavelengths, 596, 642, 705 nanometers. Basically, the range, the visible range, 550 to 750 nanometers. Of course, these transitions also depend on the lattice in which the element stays, right? So there's a host lattice. That means you call it a host lattice. Zinc oxide is a host lattice because it is hosting the dopant element. You see, this is what happens. So in the normal case, when no doping is there, you have the valence band and the conduction band, and you can only have this band-to-band transition. You can pump carriers from the valence to conduction band, and if there's a transition happening, so all these are band-to-band transitions. So transition that corresponds to the energy difference between the top of the valence band and the bottom of the conduction band, or it could be vibrational levels that are present in the conduction band to the bottom levels, right? But here, by bringing in an element like samarium, see, you create these mid-band gap states. And there are some of these transitions will be active depending on the host lattice. In a given host lattice, um, this one and that transition may be active. Yeah. And in some host lattice, all these four transitions are possible, right? It depends on many factors, the amount of dopant, the crystallographic aspects, and the thermal energy of the lattice, and the crystal field effect of the lattice on the dopant or foreign element. So all these factors have to be taken into consideration to see what kind of transitions. There are multiple transitions possible in a samarium ion, right? Samarium goes as a 3+ ion. So these multiple transitions, depending on these emission conditions, only a few active transitions can happen depending on the host lattice. Okay. Now you see this. How do I know that the mid-band gap states are created? This is very simple. I just do a simple absorption study. So you have the valence band, I have the conduction band, and when you do absorption, you can do absorption, transmittance, to find out the so-called band edge, right? So when you're shining radiation of different wavelengths, okay, measuring the intensity, what you see is at this point there's a sharp rise in the absorption edge, and that is also the band gap. So until that wavelength, there is no foreseeable intensity. That means there is no transmission happening through the system, but suddenly from the band edge onwards, you see the transmission intensity increasing. Okay, so this is a band edge. Typically, this is a band edge, and you can, depending on how sharp it is, you can calculate the band gap of the material, the optical band gap. And the blue one is typically what you see in the undoped cases. So these lines I'm showing here are created because they're the mid-band gap states. No, so the dopant element brings about all these mid-band gap states. Now here there are so to start with, a pure lattice that doesn't have any impurities in it. So the mid-band gap states are not there. So you get the blue plot. But the moment the mid-band gap states are there, you see these additional absorptions that you can understand, right? So it's a band-to-band absorption, and you also have absorption and transmissions or electronic transitions happening not only from band to band, from the conduction band edge to some of these levels, right? And there may be transitions between the levels also, right? That's also possible. So all this leads to the creation of these mid-band gap states. And from these, you see that there's a typical dip in the plot there. So you'll be able to find out what kind of transitions are responsible. You can exactly pinpointedly say that, yes, in my system, in zinc oxide doped with samarium, these are the transitions that are giving rise to these three wavelengths. For example, if this is orange, red, and deep red, right? In this range, if you also go to 540 nanometers, right? 550 nanometers, it's green, and below that wavelength, 420, 430, 440 nanometers, you have blue. If blue is also there, and if you have emission happening in a solid, for example, in all these wavelengths, then the combination of all these different wavelengths leads to white light emission. Because white light is basically a combination of all different colors. No? So that's how light emission happens in solids in a very interesting way, and these properties can be tuned, and the transparency can be altered with doping. Okay, so vacancy, the fraction of vacancies that are present in a solid can be estimated. Of course, we are really not interested in edge and crew dislocations. Of course, even though they should also bear a definite crystallographic relation with, the lattice. Elimination of these defects is possible. And coming back to the point defects, the Schottky and Frankel defect, the vacancies and interstitial atoms. So the fraction of vacancy formation is exponential minus EF by KBT. EF is the vacancy formation energy. So every compound has a vacancy formation energy. Okay. Now again, the same example that I've shown earlier in a different way, that's a vacancy, and that's a atom. And in a solid, because the diffusion can happen. So there's what is called self-diffusion. Self-diffusion happens because of the presence of vacancies. So an atom from the regular atomic position can make a transition to a vacant position, right? Thermal energy is always there. The room temperature thermal energy, KBT equivalent of room temperature thermal energy is about 26 millielectron volts. It is very difficult to see diffusion happening at those temperatures, but at elevated temperatures, diffusion is always there in bulk materials, nanomaterials, and thin films. Right? Vacancy diffusion is always possible. Now, you also have interstitial diffusion, right? Diffusion of the interstitial. Now, we know that diffusion is basically a time-dependent process, and it's all about how fast the diffusion or the mass transfer occurs, and this rate is expressed as as a diffusion flux. Diffusion. I also mentioned earlier that whether you deal with gases and liquids or solids, diffusion process is present in all these three different forms of matter. It's a very important phenomenon. Diffusion can be caused by thermal gradient, electric field gradients, magnetic field gradients. Everything is possible. So the rate is expressed as diffusion flux. Diffusion flux is defined as the mass or the number of atoms diffusing through a perpendicular diffusing through a cross-sectional area perpendicular to the diffusing species of unit area of cross-section, right, of solid per unit time. So in mathematical form, it is given in that way, right? You can see that, right? Okay. Now, yeah. So your J is 1 by A times dm by dt. The unit of J, the diffusion flux is kilograms per meter square second, or atoms per meter square second. So the concentration gradient plays such an important role. Unless there is a concentration gradient, there is no diffusion. Okay, so this is dC by dx. I can write it as Ca minus Cb by Xa minus Xp. The concentration difference between 2 points A and B, and at a distance separated by between points A and B. Right? You're looking at the diffusion between 2 points A and B, and you also need to have concentration gradient between those 2 points in order to for diffusion to happen. So the whole process of diffusion is governed by the well-known Fick's law, okay, which is J is equal to minus D times dC by dx, or dou C by dou x. You can write it in that form also. D is the diffusion coefficient in units of meter square per second square. And, you know, the Fick's second law is what is called a rate determining equation. It tells you in one way the rate of diffusion of species. That means it also gives you information about how much time it would take for diffusing species to diffuse in a given lattice, whether it is a bulk. If you're dealing with a bulk material, you have a bulk diffusion, you have surface diffusion, you also have diffusion through grain boundaries. 3 different types of diffusion. And in thin film, since the bulk of it is very thin, you normally talk about diffusion in the X and Y directions, and of course the Z, the thickness is very small. So that is the second law of diffusion. Dou C by dou T is equal to D times dou square C by dou X square. So second law of Fick's is always the rate determining equation. Now this chart shows you a number of plots of different elements diffusing in different host matrix. Now you have diffusion coefficient given in units of meter square per second, and this is 1 by T. Now, you see, what you see here is this should be, which is diffusion coefficient. It has to be, this is your carbon diffusing in alpha ion, carbon in gamma ion, zinc in copper, iron in gamma ion, and iron, Fe in alpha ion, copper and copper. This is, a typical example of self-diffusion. You see, every species diffusing in a different matrix, it has different diffusion characteristics. So the diffusion coefficient can be easily measured using this formalism. Okay. Now this data, diffusion coefficient is, of course, meter square per second. Meter square per second there. So you have all these species, iron, and then you have Fe. So the host metal, these are all the host metals. These are the diffusing species, right? And you have the pre-exponent and the diffusion coefficient values calculated, and these are the activation energies of diffusion. So many electron volts per atom, or kilojoules per atom. See? This is just to show you the kind of diffusion mechanisms, processes that happen in different host lattices by different diffusing species. And copper and copper also, the copper atoms inside the copper metal also can diffuse. This is called the self-diffusion. Okay. Now, the concentration profiles for a non-steady state diffusion taken at three different times, T1 and T2 and T3. The concentration, obviously, the time of diffusion is also dependent of on temperature. The larger the higher the temperature, and you have the diffusion happening in the same material system at a faster rate. Okay, so that means the temperature obviously plays an important role. So the ceramic material like barium titanate, which takes about I said the overall process of mixing, grinding, heating takes several cycles of heating. All that you're doing to make the species diffuse, form new compound in a homogeneous manner. And of course, that whole process you can hasten up by increasing the temperature, not to the extent that you melt the system, right? So if that heating process is done at a lower temperature, it takes longer time for the final phase to form. That's what it means. So very quickly, this is all standard textbook stuff, copper nickel diffusion couple, it is called. So you form the couple. This is how I started explaining about how diffusion happens at an interface. And if you have a couple like this, that's the only path through which diffusion can happen, right? There's only one interface, so the one nucleation site at which diffusion can happen. Okay. Now, yeah, this is at before the high temperature treatment. After when you subject this couple to high temperature treatment, you expect nickel going to the other side and copper diffusing to this side, right? And yeah, so diffusion of copper atoms and the copper nickel alloy forms in that process, right? But if you provide only one interface, it's going to take a lot of time. And this is again an example of how the intermixing happens, and this is a typical concentration profile also. So if these are two junctions and at a given temperature at different times, I can look at the profile. There are also methods now to find out what amount of diffusion has happened in a given amount of time. See, diffusion and nucleation are two main processes that determine the growth of polycrystalline materials, single crystals, thin films, right? Okay. So, yeah, that's what I've shown there. Copper nickel diffusion couple after a certain temperature treatment, showing the formation of the alloy, right? And diffusion of copper and nickel atoms within the couple, and the concentration of copper and nickel as a function of position across the couple. To quickly look at this problem, a plate of you take a plate of iron, it's exposed to, say, a carburizing atmosphere, that is carbon rich atmosphere on one side, and a decarburizing carbon deficient atmosphere on the other side at 700 degrees centigrade, right? Now, if a condition of steady state is achieved, calculate J, the diffusion flux of carbon through the plate, if the concentrations of carbon at position of 5 and 10 millimeters beneath the carburizing surface are 1.2 and 0.8 kilograms per meter square. Okay. You can assume that the diffusion coefficient of 3 into 10 raised to minus 11 meter square per second at this temperature. So if you do this simple problem, your J is equal to minus D times the concentration gradient, that is Ca minus Cb divided by Xa minus Xb. D is given there, that is 3 into 10 raised to minus 11 meter square per second. That is a diffusion coefficient. And then you can substitute these values and you get the final value as shown there. That's a diffusion flux. Now, if you are asked to determine the composition in atom percent of an alloy that consists of 97% of aluminum and 3% of copper, right? Composition. Now the copper. Yeah, this is not Cu. Cal is 97, and Cu is 3. So take it as Cal and Ca. Okay. Now the C prime of Al is the modified version is that times 100. So that gives you modified concentration as by substituting all the parameters there, you get it as 98.7%. And similarly, when you do this calculation for modified concentration of Cu, it is 1.3 atom percent, right? This is again simple way of determining the composition in atom percent, right? See, you talk about 97 weight percent of aluminum and 3 weight percent of copper. So 97 to 3 in terms of weight percent. For the atomic percents, if you want to calculate the atomic percents, this is the way to do. Okay. So that's where you bring in the atomic mass of each of those constituent elements. Then only you get the actual atomic percent, which is always different from the weight percent. Weight percent wise, it is 97 and 3. And here you see the a concentration of aluminum is 98.7%, and that of copper is 1.3%. It's not exactly in the 97 to 3 ratio. Okay. Now, this is an additional plot to show that that's how the concentration gradient can change. This is just to show you that this part, sometimes, yeah, this is the distance from the interface. Okay, I'll come back to this plot a little later when we talk about thin films and interfaces and all that. You'll probably understand better at that point. So basically, thin film growth is all about nucleation. We need to nucleate the the atoms, and this nucleation has to be uniform. Then only you get a completely a uniform layer, and making those thin, uniform, homogeneous layers is always a challenge. This depends on many factors. It depends on the nucleation. It depends on the temperature that you provide, the thermal energy that you give. It depends on the substrate. And in some cases, it depends on the pressure environment also during the growth process. And it depends on the substrate, because you're bringing these atoms and then you're making these atoms to rearrange themselves on a substrate. Substrate, of course, is a base material. But substrate is a single crystalline material with a fixed lattice constant. So to start with, the surface energy of the substrate dominates. This is a very important point. So that basically determines the first part of nucleation, right? You'll understand all that as we move on. So this is a typical example. It's easy to show it in this nice schematic form of alternating layers of cobalt and nickel. You see, I have those red balls, cobalt, nickel, you know, a single layer of cobalt, 2 layers of Ni, and so on, right? And in reality, to get this type of growth requires a lot of sophistication in the growth process. This is when it comes to alternating metallic layers. But again, another big challenge when you come to multi-component systems, right? You have a substrate, and I'll come back to this and explain at a later stage. To form thin films of such complex systems, this is a superconductor, yttrium barium copper oxide. What I have shown is 4 unit cells, 4 unit lattices, unit cells of this wonderful material. This is the high temperature superconductor that was discovered in 1986. Okay, it has lots of applications. Okay, now see, one unit cell itself is so complicated. It has these planes, these chains. You know, these are the conducting paths, and a long C-axis, and this is a B-axis. These are just 4 unit cells I have shown there. Now imagine all such a complex structure, getting it in the form of a single crystalline growth, that is epitaxial growth form. It's a big challenge, right? That's where you get the right method. So to grow these multi-layers of CO and Ni, a normal sputtering technique may be okay, but then to get epitaxial layers of these multi-component oxide systems like yttrium barium copper oxide, the same method that you use for the growth of these metallic layers may not work. So you need another method. You know, this is a good example. The crux of why we need thin film growth. No, yttrium barium copper oxide is an unconventional superconductor. It's actually a ceramic material. By doping, it acquires metallic properties and it becomes superconducting. Now, a superconductor, from the superconducting transition temperature and below, it doesn't show any resistance to the flow of current. We know that, right? So in yttrium barium copper oxide, the superconducting transition temperature is 90 Kelvin. So if you measure the resistance when a current is flowing, the current meter, the voltmeter reads 0 volts because there is no resistance drop in the superconducting state, right? So in the superconducting state also, the current carrying capability is normally much higher than the current carrying capability in the normal state. See, the copper and aluminum wires that are used for household appliances, you know, mostly aluminum wires. So when you turn the switch on, your electrical appliance is on, a bulb or fan, air conditioner. So these wires have to have a certain amount of current carrying capability, and so the current density rating is normally anywhere from 10⁻⁴ to 10⁻⁵ amperes per centimeter square, because these are the normal metallic wires, right? But if these wires are made of superconducting wires or tapes, then the current carrying capability should be as high as 10⁻⁶ amperes per centimeter square, almost 2 orders more, right? And yttrium barium copper oxide being a ceramic that has grains and grain boundaries, you see, in a polycrystalline form, if you say a polycrystalline form of yttrium barium copper oxide, the polycrystalline system has grains and grain boundaries. The current density is hardly 100 amperes per centimeter square. Whereas the current density of a thin film is, 10⁻⁶ amperes per centimeter square, almost 4 orders of magnitude more. Why? Because, so let's say I got a thin film of yttrium barium copper oxide superconductor, and the thin film itself is polycrystalline in nature. That means large number of grains and grain boundaries. Obviously, when the current is flowing, there is a large amount of grain boundary resistance. But when you grow a completely epitaxial thin film, it's a single grain boundary. There is no hindrance to the flow of current, which means all these current carrying paths are right uniformly arranged and in a way that there are no misorientation. That means you have a small current carrying path. If the grain boundary is there, the current carrying path is lost, then it continues in the next region and so on. Right? That problem is there in this case, but not in that case. And a simple way to explain this is the following. So in a polycrystalline thin film or a bulk material, when a current is passed through, right? So each of those regions, of course, is crystalline, right? And each of those grains, say, offer some amount of resistance to the current flow in the normal state. Okay. Now you see, I've named them as R1, R2, R3, R4, R5, different zones with different resistances. These are all they can be considered as series resistors, right? But the current has to also surmount that barrier, that grain boundary resistance, which is very important. Okay, and the grain boundary resistance is always very high. And so when you pass a current through a thin film or a single crystal or a bulk material, current always flows through the least resistive path. So when there is a huge resistance barrier, it either if the input current is sufficient enough to surmount the barrier, it's fine. Otherwise, it has to find a least resistive path. Okay, and this is now easy to understand what I explained in the earlier classes. Now, rho versus T for a semiconducting material, you measure it in the thin film form, crystalline form, and a bulk form. Now you can find out which belongs to the single crystalline form and which belongs to the bulk form. And obviously, the one with the polycrystalline nature shows more resistance because of the inclusion of the grain boundary resistance. You see how nicely a physical property is correlated with the microstructure. See, there's always a correlation between physical property and microstructure. So the structure property correlation is extremely important. So why thin film growth? The thin film growth is the answer for authentic physical property studies and device applications. So authentic physical property measurements means if I want to do measurements on say high quality thin film of a semiconductor or a superconductor like yttrium copper oxide, I would like to get this material in the best possible crystalline form, either in a single crystal form or a thin film form. Now, this is a classic example. Yeah, the same material, I can get it in an extremely smooth crystalline form or in a polycrystalline form. The problem with polycrystallinity is the grain boundary, which is presence of grain boundaries, which is detrimental to physical properties. And you see, higher resistance to the grain boundaries, your resistance shoots up. And that's what it is. The crux of the whole thing is the answer for authentic physical property studies. And today, in every device, materials in thin film form are used, and then that is actually helped in a big way in the miniaturization revolution. 15 years back, when the mobile phones came into the market, they used to be really bulky, and now everything has shrunk. And our TV screens are the size of the thickness of the TV screens, or laptop screens. Everything is shrinking. The whole size of laptop is so small now. That's because of the device capabilities of all these materials in excellent quality thin film form. So the thin film processes have improved. The characterization techniques have improved. In situ processes have improved. So it's a revolution from many different fronts that has led to the present day you know.